Hello, everybody. Today we're going to look at some actual physics vocabulary terms to get started on learning physics. As we go along, any other math skills that we need to review, we will review as we need them. Okay, so the definitions that we're going to be looking at today. The first one says, describes and explains how the universe works. Well, that is physics. That's what we do. We're going to learn how to describe and then explain how things work. Before you can explain it, you need to be able to describe it. If you can't describe it, there's no way you're going to be able to explain it. All right. Then there are three definitions we have to know. It's part of the state standards, but these are three terms you already know, so it's not going to be too difficult. The first is, if you have a possible explanation or solution which has not yet been tested, you haven't done any experiments, taken any data, nothing. All you've done is propose an explanation or solution. This is called a hypothesis. Now, see, you've heard that term before, haven't you? Okay? All right. Now, the next one. The synthesis of a large body of information which explains how laws and hypotheses describe certain aspects of the natural world. Okay, this is called a theory. Okay, for example, the theory of evolution is a large body of information and explains how laws and hypotheses describe certain aspects of the natural world. In this case, how things change. For example, the theory of evolution uses survival of the fittest. The theory of evolution also talks about the fact that man and apes have a common ancestor. Man did not come from apes. Darwin did not ever say that. He said they had a common ancestor. Then there's also adaptation. That's another part of the theory of evolution. So it's a synthesis, a body of information that works together to explain how things evolve or change over time. Finally, a hypothesis that has been tested over and over again and found to be true in every possible situation can, by agreement of the scientific community, be exalted to the grand status of a law, such as the law of gravity. But now understand, laws are specific. They only describe one particular thing. For example, the law of gravity only describes the fact that one mass will attract another mass. It does not explain why that happens. It just says that it always does. That one mass will always attract another mass, and that attraction is called gravity. But it is a law because it was a hypothesis that was tested over and over and over, and it's always true, so it is now a law. Okay, so laws describe physical phenomena. Theories explain those descriptions. Okay? Now, let's see. A process for discovering scientific relationships. A process. A method. Oh, they're talking about the scientific method. Okay? All right, and this method is based on observation, experimentation, and analysis. Okay? And, of course, you can look it up to see, and depending on which part of the scientific community you come from, you might have a different answer. But technically, Galileo is the person who's first attributed with coming up with a logical process for doing experimentation. Galileo, Galileo. Galileo. Okay? In fact, that was his first name. I'm not sure if you guys realize that. He was from Italy. Galileo Galilei. All right? So that's his first name. We'll talk more about him later. Now, the scientific method. All right? Most of you all have heard this before. Mrs. Alo taught it to you. A lot of your other science teachers teach it to you. And because it's state standards, I have to do it too, even though you might know it very, very well. So if you printed out your other handout, we're going to take a look at reference page 7. Okay, and I need to put the R7 right there so we have it. All right, we're going to take a look at the 6 most common steps of the scientific method. Now, there can be up to 12. Scientists tend to modify the number of steps according to how complicated or how easy the particular experiment they're doing is. But these are the 6 most common steps. So let's take a look. Notice they are rather wordy. So we're going to learn how to paraphrase them to make life easier. The first one says when you have a physical phenomenon, you first need to observe it. Okay, you need to see what it's doing. So basically, we're just going to say, oh, let's observe the phenomenon. Why write the phenomenon? We know it's a phenomenon. Okay, so maybe you want to look at, I'm trying to remember some of the science experiments for the science fair. Okay, maybe one was different shapes of hulls of boat and how well they can go through the water. So the first thing you would do is you would observe a boat going through the water and look at the type of wake it makes and how fast it can go for the particular body of water it's in. And you might describe how big it is, how deep it is, how wide it is, the hull of the boat, that is, not the water. And think about some of the things that affect it. The next thing you would do, after you've observed your phenomenon, you would formulate your hypothesis to explain the phenomenon that you're interested in. Now, that's kind of wordy, so we're just going to say form hypothesis. That explains it right there. So we're going to first observe and then form our hypothesis. The next thing we're going to do, once we've got our hypothesis, then we need to take quantitative measurements. Now, if you remember the difference between quantitative and qualitative. Qualitative means words, quantitative means numbers. So that means you're going to collect data. So it says make quantitative measurements of the observations. Guys, basically you're going to take or collect data. You can use the word take data. You can say collect data. It doesn't really matter to me which one you use, take or collect. All right, now, so you've taken all this data based upon your observations and the hypothesis you formulated. Now that you've got the data, you need to do one thing, and that's evaluate the hypothesis that you made with the data, the measurements, okay? You're going to basically, if you're going to evaluate, that means you're going to compare. Look, there's no E, there's no T there. What am I, oh, I think I was going to write the. Compare the hypothesis. Compare the hypothesis with the data. That says it a little easier. Okay? Now, when you make a comparison, you're either right or you're wrong. Okay? It either compares positively with your hypothesis or negatively. One or the other. So that's what these last two are about, whichever way it goes. So let's take a look. If the hypothesis and measurements disagree, if you get negative agreement, Then you have to return to steps 2 and 3. Maybe you want to modify your hypothesis, or maybe you think the kinds of data that you took weren't good, that maybe you should have taken it a different way. And so you're going to redo it. You're going to go back and see if you can fix something and take data again and see if it agrees then. So if, and in this case, I'm going to say they, because we already know we're talking about the hypothesis and the data. If they disagree, and instead of saying all this, I'm going to say start over. How about that? Okay? So if they disagree, start over. Now, on the other hand, if they don't disagree, then they must agree. So look right here. If the hypothesis and measurements agree, then you're going to report the confirmation of the hypothesis to the scientific community. So let's paraphrase that. If they, I keep forgetting them. We're paraphrasing, so I'm putting parentheses around it. Okay? If they agree, then report it. You can say report the confirmation, or if you wish, you can just say report it. Okay? So, you're going to observe the phenomenon so that you understand what you see happening. And then, from that, you're going to form your hypothesis. And once you have your hypothesis set, then you need to take or collect data, measurements. Then you need to compare the hypothesis that you formed to the data. You need to analyze. That's what analyzing is, comparing. Then, if they disagree, you're going to start over, either with your hypothesis or your data. You're going to start over. But if they agree, then you're going to report it. Okay? And guys, that's the scientific method. All right? The basic premise of the scientific method. Okay, now back to our definitions. All right, we've looked at the scientific method. Now let's look at a few more definitions we just need to be familiar with. And these you've seen before. Well, the majority of them. Okay, first off, any quantity that has properties of volume, mass, inertia, and gravity. Okay? And that would be matter. Matter is the stuff. It takes up space. It has volume. It's made up of stuff, atoms and molecules, so it has mass. It has a property called inertia, which we'll talk about in a minute. And it also has a property called gravity. It always attracts other masses to it. Okay, matter attracts matter, and that's gravity. Okay, but what is this one right here? What is this inertia? Well, inertia is a property of matter that resists change in motion. In other words, if you're in motion at constant velocity, your body wants to continue to travel at that velocity in a straight line. It doesn't want to change. It resists change, and that's called inertia. If you've ever tried to run down a big hill, when you get to the bottom and try to stop, you realize it's a little hard, okay? This is also the reason why we wear seat belts in the car. When you step on the brake, if somebody were to pull out in front of you suddenly and you had to slam on your brake, the braking force is not applied to you, it's applied to the car. So if you don't have a braking force applied to you, your body wants to continue forward, in this case through the windshield. Well, that's not very good for us. So we wear seat belts in order to transfer the braking force to our bodies as well, so that we slow down with the car. So inertia, it is a property we have that resists change in motion. Okay. Let's see, the next one. Any length, area, or volume that can be measured, okay? That is called space. And no, it does not have to be empty. It can have matter in it. A space can have matter. The room that I'm sitting in right now has a volume, and it contains matter. It doesn't have to be empty. All right, the continuous passing of events. Ooh, I wonder if you can guess what that one is. It's actually pretty simple. Dun, 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 dun. Get it? It's time. Okay, time is the continuous passing of events. We can't slow it down, although sometimes it does seem like it drags. We can't speed it up. We can't go back in time. We can't go forward in time. Time marches on at a continuous rate, okay? We can't change that. Then, let's see, the ability to do work. Oh, this is another major component of the universe. It's called energy. This is something you learned back in middle school science. If anybody remembers that definition, we still use it today in physics. It's the ability to do work, okay? Now, 4 of the definitions that we just wrote down are actually quite important, okay? So I'm going to circle them, and then we're going to see what they are. Matter, space, time, and energy. Now, these 4 items, if we connect them, these 4 items are what we call the 4 fundamental components of the universe. Everything in the universe is made up of these 4 things. Anything that exists, it's either matter, or it's a measure of space, or time, or it's energy. There is nothing else. That's it. That's all there is. Matter, space, time, and energy. Everything falls into one of those 4 categories, okay? And we're going to be learning how these 4 components interact to create the physical phenomena that we see. And they're measurable, so we'll be able to take data. Kind of cool, okay? All right, now, the next one. Trying to get through this as quickly as possible so we're not sitting here forever. The next one, it says numerical information about the size of an observed object or event, okay? Numerical information about how big something is. Oh, well, guess what? That's a measurement. That's a measurement, okay? And we're going to be taking lots of measurements, one way or another. I'll figure out a way for us to do it, okay? Now, the name given to a specific chosen amount of a measurement of a quantity. All right? Well, that is called a unit. In other words, when I measure the length of a table, and another person also measures the length of the table, how do we compare? What size chunks did we each measure with? Well, that's what the unit is. It's the chunk that you're measuring with. Length can be measured in chunks called meters. They can be measured in chunks called inches, or maybe feet, or centimeters. There's all different size chunks or units by which length can be measured. Time is the same way. You could look at chunks called days. You could look at chunks called minutes. You could look at chunks called years or seconds. So a unit is simply the size of chunk that you're going to measure with. Now, some units are actually measured in terms of other units. And an example would be the unit for energy. Energy is measured in a unit called a joule. But a joule is not a fundamental or most basic unit. It is what we call a derived unit because it has to be measured in terms of other base units. So, for example, 1 joule is equivalent to 1 kilogram meter squared per second squared. Okay? So it is composed of this particular combination of SI base units, okay, or fundamental units. There we go. So, in the back of the textbook, which of course we don't have right now, but we'll see what we can do, they list all the fundamental SI units of physics and the derived units and what fundamental units they're composed of. All right. Now, let's look at the next thing. A specific amount of a quantity chosen to represent the unit size. Okay. In other words, if we're measuring the table and we're using meters, how do we know how big a meter is? Who said that a meter is going to be a certain size? What did they choose to represent the size of what everyone now knows a meter to be? Okay, it's called a standard. You have to have a standard in order to know how big your chunks are always going to be. So there is a standard by which we know how big all meters are supposed to be. There is also a standard for how big all kilograms are supposed to be. There's a standard for the second of time. There's a standard for a lot of different base or fundamental units. And we're going to be looking at some of them right now. But this is how we know how big a particular chunk is supposed to be. Somebody chose something to represent that size. And we're going to look at them in just a minute. Let's get this last definition though. The last one is the system of units that we're working with in physics. Now, in chemistry, when you were in chemistry, you didn't use big stuff most of the time. You used little bits of things like grams of dry powders or milliliters of a liquid. But in physics, we tend to work with the very big. In chemistry, because you worked with the small things, you worked in a system called within SI called the CGS system, centimeter, gram, second. And all of those three units work together in the formulas to give you the answers you needed. But in physics, because we work with the big, we don't want to use itsy-bitsy centimeters and grams and stuff like that because our numbers would be huge since those are such small quantities. So instead, in SI, we use what's called the MKS system because we use meters and kilograms and seconds. All right, big measures. So, MKS system. All of the units that we work with, including the derived units, are these right here. Meter, kilogram, second. Okay? If we use something else in the physics formulas, we won't get the wrong answer. If we use centimeters with kilograms, we're not going to get the right answer. If we use hours with meters, we're not going to get the right answer. Okay? So all the units that we plug into a formula have to be either meter, kilogram, second, or derived from meter, kilogram, and second, like the joule. All right, finally, real quick, right here, this is a little table, and I've already filled it in so we don't have to take tons of time doing that. Here's our 4 fundamental quantities, all right, matter, space, time, and energy. They are measurable. We measure the mass of matter. We don't measure inertia. We don't normally measure the gravity to see how much mass there is. We look at or to see how much matter there is, we look at the mass. We measure the length or the distance of a chunk of space. There is no special word for the property of time. It's just time, and same for energy. It's just energy. So now, each one of these in an equation or formula, this is the symbol we would use to represent each of these. An M for mass, L or D for length and distance, lowercase t for time, not capital T. That means something else in physics. And a capital E for energy. Those are what we would use in the formulas to represent these quantities, these properties. But at the end of the measurement, is the unit by which it's measured. So kilogram of matter, meter of space, length, or distance, seconds of time, joules of energy. And these are the symbols for the units. And they're always found at the end of the measure. Okay? So for example, a variable symbol, F equals MA, so there's mass, M for mass, right? But if we were looking here, we might say 1,000 kilograms. There's the unit. It goes at the end of the measure, okay? Now, how do we know how big each of these is supposed to be? Because somebody had to choose at some point in time how big these were going to be. So today, all of the standards for SI units are kept at the International Bureau of Weights and Measures in Sèvres, France. So in France, you would go into the International Bureau of Weights and Measures, and you would see for the kilogram, somebody lopped off a chunk of platinum iridium alloy. It's a cylinder shape. And that particular chunk of material represents 1 kilogram of matter. Okay? 1 kilogram of matter. Now, when companies that make the brass weights that we sometimes use to do experiments with, they had to make sure that the 1 kilogram masses that they produce for science teachers all over the world have the same amount of mass as that cylinder of platinum iridium alloy, or they wouldn't be a kilogram. Get the idea? This is the standard, and we compare all other measures of the kilogram to that. The meter. There have been a lot of definitions of the meter over the years. This one is based upon the speed of light, which never changes. I'll tell you more about it later. Maybe I'll put on a separate little video about the meter because it's kind of interesting. But it's now defined as the distance light travels in a tiny fraction of a second. What fraction? Well, it doesn't really matter. You can look it up, but it's teeny, 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 tiny. And how far the light can travel, how far it can travel in that tiny fraction of a second, that's 1 meter. So that's why a meter stick is as long as it is. That's how far light travels in that tiny fraction of a second. Time, the second of time, it's based on the amount of time it takes for a large number of vibrations of cesium atoms in an atomic clock. Cesium atoms vibrate at a regular rate that never changes. So they base the second of time on the number of vibrations of that. The joule, since it is a derived unit, it has actually no standard. It is measured mathematically in terms of the others. In other words, you have to calculate it. All right, boy, that was a big one, and I've talked fast, and I'm sorry, but I didn't want this to take too much time. If you need to go back through and listen to something again, be my guest. Do so, okay? And if you have any questions, please leave them in the discussion box that this note set is found in, okay? All right, bye-bye.